Alright, so here we have extra creamy whipped topping, and it's really important that we get it with dairy. So there's like a little icon that says it's with dairy. So we're going to go ahead and put that into a bowl, and then after we get this in a bowl, and this is important because it has, the dairy part's important because it has those casein molecules. And then after that, you get 1 can of sweetening condensed milk. And you just pop that right in there. Alright, now that I've got all the yumminess in there, I'm going to go ahead and stir that up. So I have here about 1 lemon. So I just took this lemon and squeezed the juice out of it, or put it in my blender and strained it. And so here is the juice of about 1 lemon. I'm going to add that to it as you mix it in. And this is important because it's dropping the pH. So it's something really acidic. Lemons are really acidic and kind of sour. And so we go ahead and add that in. And I've got a couple seeds in there, so someone's going to be lucky when they get that. So then I go ahead and take this pie crust here. So I already cooked this. It was just a pre-bought pie crust. And I'm going to go ahead and drop this in here. And you can already see that it's a lot thicker than a typical cream already because of those casein molecules in the pH that they're in. There's some reactions that go on. And so we just mix this in. And then after this, all we have to do is we just cover it with foil. So you just want to make sure that that's nice and pretty looking. And then you just cover it with foil and stick it in the refrigerator overnight. Alright, so this is the pie from before, and you can kind of tell that it's just definitely a lot thicker than it was before. It's like an actual pie now. So, bon appetit! Alright, so let's talk about the chemistry behind the lemon pie. So actually, the recipe that I found actually calls for limes, and I used a lemon. But in the McGee book, it actually talks about how limes are 8% of its weight is actually acid, so like citric acid. And in lemons, it's about 5%. So I believe it was like a half a cup or so is what it called for, and I used a whole lemon, which is probably a little bit more than a half a cup. So the acidity was able to actually balance out because this acid is actually what is making that structure like coagulate. And kind of break those fat globules like we were talking about in class a little bit when we made butter. So the sweetened condensed milk also that we used, so 55% of that is actually just sugar, which is kind of crazy if you think about it. It's mostly sugar. And then the rest of it is basically just a supersaturated solution of fat. So we actually talked about this in class as well, but supersaturated solutions are basically where you just take the water out of it. So milk has like a lot of proteins and fats and different things like that, and that's all that's basically in this, with just a tiny bit of water left over, maybe not, but not much at all. So it's mostly just fat and sugar that we added to it. Also, we had heavy whipping cream. So heavy whipping cream actually has more fat than other types, than a light whipping cream, I guess. So 38 to 40% of whipping cream, of the heavy whipping cream, is actually fat. So that's another reason why we might want to use that instead. So we also talked about a little bit in class how you can beat in the air when you beat it in as well. So I mean, obviously you saw in the video I wasn't beating the tarnations out of the cream there, but still there was air in there, and it was able to build up the air and little air pockets and stuff in the heavy whipping cream already as well. And then we stored it in the fridge so that as the structure, so as these fat globules they broke, and as they're reforming new formations to try and stay away from the hydrophilic areas, so the hydrophobic away from the hydrophilic and different things like that, and as reforming those structures, it actually it's better in the cold because then not as many air bubbles will be bubbling out of it. And that's why you store it in the refrigerator overnight. And then also, when you add acidity to it, it breaks it down and breaks these fat globules down a little bit faster, and that's why we were able to basically just add acid to it and throw it in the fridge. So it's a lot like the experiments we've already done, but just a different approach. Alright, so here we've got some beans, and we just washed them, and they're just the regular old black beans, as you can kind of hopefully see without me spilling too much water off the top. But we're going to go ahead and just put those straight in the pressure cooker, and I didn't soak these at all because I've got a pressure cooker that's amazing. And then I've got some water here, and I've already put some spices in there as well. And if you can just come up here just a little bit, so we can kind of tell. You want excessive amounts of water over those beans for sure, so it doesn't explode in a pressure cooker. So right here I've got about 2 fingers width, and that'll probably be enough water on top. So then we close this and put it on pressure. It's plugged in. That's the important part too. And then I'm going to go high pressure for about 30 minutes. And then actually after the 30 minutes, my pressure cooker is kind of cool because it'll actually automatically release the pressure over time, and so that's why it can actually cook it for less time than other pressure cookers sometimes. But anyway, so we just hit start, and we just wait for it to cook, and we'll come back afterwards. Alright, so we just barely cooked these beans, and I actually just left them so that they would so all the pressure's out of the pressure cooker. And you can kind of see these beans now, and they are ready. They're super soft and delicious. And so I'm just going to add a little cornstarch and thicken that sauce up, but you definitely don't have to do that. And a little salt too to make them taste good. Anyway, thanks! Alright, so for the chemistry of beans, so we cooked it, you saw that I cooked it in a pressure cooker, and so pressure cookers can actually cook at higher temperatures. So right now we're at like atmospheric pressures and different things like that, just the atmosphere of wherever we're at, whatever altitude we're at. Well, in a pressure cooker they can actually condense it, and so there's a lot more pressure in there. And so because of that, the temperature that water boils actually is a higher number, is like a higher value than at regular boiling point. So, for instance, typically we can boil water at about 212 degrees Fahrenheit, and in a pressure cooker you typically get up to about 250 degrees Fahrenheit. So things actually cook faster in a pressure cooker. Beans are actually semi-notorious, maybe, for giving off flatulence. So they contain large amounts of carbohydrates that we actually can't digest with the different acids and different things that we have in our stomachs. And so it gets cleared down into our intestines, and then bacteria inside of our intestines are actually the things that break it down for us. And so all these really big carbohydrates that we can't really break down are actually giving off gases later in our large intestine because the bacteria give off gases when they digest these enzymes for us that we have in our bodies. So the two types of big carbohydrates that we have, there's oligosaccharides, which are just like 5 or more sugars linked together in different ways, and then there's also the cell wall cement. So like part of the outside, like the fibrous part of the bean here, is what we're talking about. And so anyway, so both of those actually get broken down, and there's actually twice as many cell wall structures than there are oligosaccharides. So there's an enzyme called lipooxygenase, and this is the structure of the enzyme right here. and it actually breaks down unsaturated fatty acids into small and odorless molecules. They become active when there's enough like oxygen and water present, is what actually is able to drive that reaction forward. So here we have some structures as well. We have hexanol, cis-3-hexanol, and oxanol. So these structures here are actually structures that what McGee says gives it beaniness, or it's like it's bean-like flavor. Are those three structures right there? Basically, when the proteins, or when the fats can degrade and different things like that, it gives kind of that taste to it and breaks down into mainly these three chemicals. So how we actually break it down is the bean here. So it has to be filled and totally saturated with water to be able to happen. And it's really, really difficult just because of the way that the cell walls are structured. Like hardly any water can come in and out. And actually, a little bean anatomy for you. There's a helium right here. So there's like this little pore that allows water in and out and different things like that. The only place where the bean will actually diffuse water for the first 30 to 60 minutes. So it's kind of crazy. If you put it in water, it actually won't swell for 30 to 60 minutes with water, even though there's so much more water than there is inside. And then after that, the outside of the bean will actually start to allow water in, and so the beans will start to swell. So that's fantastic, when we want to cook it. It takes a really long time, but then afterwards we don't want to go too far as well. So like if we're done cooking it and we want to reheat it or something like that, we don't want to cook it too far, which typically is not an issue, but different things that you can do to preserve it so it doesn't do that and doesn't explode or doesn't go bad as well, is you can put it in acids, sugar, and calcium are three of the things that McGee suggests for slowing the softening of beans. So the reason that is they actually react with the outer cell walls of the bean, and they just reinforce the cell walls, and so the cell walls won't want to break as easily, and they won't soften up and won't let water in and different things like that. So it's definitely not something that you want to add if you're cooking the beans as well. You want to do that if you're trying to preserve them. So faster ways to cook the beans is we might want to soak them ahead of time. Now this is semi-obvious. It's just because we're allowing water into the bean. It actually takes time for that to happen, 30 to 60 minutes like we were talking about before. So if you soak the bean ahead of time, it will actually speed up the cooking process by about 25%. Also, I thought this was really interesting, that you can add salt and baking soda. That will actually increase the speed as well, because sodium will actually displace the magnesium that's in the cell wall of the bean structure, and it will make it easier to dissolve, so the cell walls will actually start breaking down a little bit, which is kind of cool. And it was really crazy. Salt at 2 teaspoons per quart. Don't make that mistake. 2 teaspoons per quart. It actually speeds it up 25%. And then baking soda at 1 teaspoon per quart actually speeds it up 75%. So next time I cook beans, I'm going to try it with a little bit of baking soda and see what happens. Anyway, that's it.